thanks for the introduction and thanks for the invitation. So I'm happy to talk here. So today I'm going to talk about written in this title, and it's based on joint work with Gromov-Witten. So yeah, let me get started. So in this talk, I'm going to care about a closed symplectic manifold of dimension 2n. And so the purpose of counting homomorphic curves, of course, we need to choose a almost compact structure. And in this talk, it's going to be omega compatible. And now let's furthermore choose the integral homology class A here, the second homology of a target manifold. So given this data, we can consider the moduli space of homomorphic maps with this amount of notation. So it's going to be genus G with k-mark points. Data to keep track here is the manifold almost compact structure together with the homology class. So defined to be, say, equivalence classes of stable J homomorphic maps. So stable. So here, sigma is a possibly nodal Riemann surface, and J is the given compact structure on the Riemann surface. And of course, this moduli space is described by require that the differential of this map is convex linear. And on this, if you look at domain, it defines a point in the number space between the G and k-mark points. And finally, we require that this curve represents homology class A. So this is our moduli space. And given this moduli space, we have a pair of natural maps given by the following. Yeah. First one is called a stabilization map, or I think you also call it forgetful map. So it just go from a stable map to a stable curve, which underlies this given map. And there's another map, which is called evaluation map, because here our curve has k-mark points. So we can just look at the value of this curve and those mark points, and that defines the k-tuple points in our target manifold. So this is just a k-fold product of the manifold. This is our moduli space. I think it should be familiar to most people in the audience. And so, okay, so we want to study these spaces. And then there is a well-structured tangent objection theory, which characterizes how these objects deform locally. So let me just write it down. So we understand this moduli space as the zero locus of some kind of random differential operator with Delta operator, and this denotes the linearization of Delta operator and a point in the moduli space represented by U. And over here, so V is chosen to be the tangent space of Taylor slice. And these are the vector fields along this stable curve, which tells you how to deform this map. And this is the space of 0, 1 forms, taking value inside the pullback tangent bundle. So this is the target and domain of our linearized operator. And of course, we know that we can call this maybe Zariski tangent space. The moduli space of homomorphic maps are just the space of kernels of this operator. And in order for this space to be smooth, we know that the co-kernel should be non-zero. Sorry, it should be 0. But in general, because of problem coming from equivalent transversality, the co-kernel of this operator is non-zero. And on the other hand, because we're looking at stable maps, they could have non-trivial automorphism groups. So if we define automorphism group, this map Q to be the automorphism of the domain, which intertwine with the map, this could be non-trivial. So because of these two properties, we know that in general, this modular space is only an orbit space. In the sense that it's a space with local model given by, say, a quotient of topological space by finite group action. So, that's finite group. Because smoothest fails, this cannot be made to manifold in general, and because of the presence of automorphism group, we have this finite group here acting on this space. Okay, so this might be a very bad space, but of course there's classical work in topology telling you that nonetheless you can define some kind of virtual fundamental cycle of your modular space. So let me write it as a theorem. And people, so Fukaya-Ono, I think, right. By Cauchy-Riemann. And recently, of course, there is a approach of Pardon and many others. So it tells us that this modular space of stable maps carries a Q valued fundamental cycle. And because we have a, say, homology cycle, and know that on this board we have the two natural maps, first one given by stabilization map, second one given by evaluation map. We can use these maps to pull back homology classes on the respective targets to define invariants. So then if we write this Gromov-Witten invariants of genus G, k-mark points representing homology class A, and I just care about primary insertions defined to be, say, the integration over the virtual fundamental cycle of the pullback of homology classes. Over here, for the modular space, we need to fix a J. But here, I don't write J as a part of data. That's because this is actually an invariant independent of J. That's part of that theorem, of course. Which tells us that this is indeed a symplectic invariant. Any question about the statement so far? Okay, no. And one notable thing here is this virtual fundamental cycle is actually Q valued. And you might ask why. Well, morally speaking, the point is if we look at some kind of space, which is more just given by a point, modulated out by some finite group action, and we give this point an orientation, it's a positive orientation, we should count it with contribution given by 1 over the order of this group. And in reality, Q shows up because of the following reasons. So in the approach by Fukaya-Ono and many others, Q value appears because one has to choose multi-value section. Sorry, multi-value sections to achieve transversality. And because it's multi-valued in the end, you need to divide out by this kind of multi-value, so Q value shows up. And in the work of Pardon, we have Q because, well, for orbifolds, which is oriented, punctual duality only holds over Q. That's the background knowledge. And then the motivation of today's talk is can we construct refinements of this kind of rational value invariants? So then the slogan for today's talk is, okay, we should care about this problem, and if we really care about that, we should do it in 2 steps. So the first one is the following. So in some sense, we want to find a universal homology theory which can hold this modular space. So the first thing by refinements, I'll talk about that later. I'll tell you exactly what refinement means. So let me tell you what I want to do first. So yeah, I mean, maybe I should explain it now. So let's say we just look at our topology. Let's say we have topological space M, and let's say we have another manifold, say M prime, mapped into our target space M. And of course, we can just push forward the fundamental homology class of M prime to define a homology class of target manifold. That's something we can do. But now if we assume that the tangent space of M, say, has a complex structure, say, you will see, I'll tell you this example. So if this is part of the assumption, then we know that this M actually defines an element M prime. In a so-called complex bordism group of the target manifold. And then, okay, well, I call this a refinement because there is a natural transformation between generalized homology theories from the complex bordism theory of the target topological space to the integral homology theory of the target topological space. And this is called the TOM homomorphism, which just sends the fundamental class representative of this bordism class to this corresponding homology class. That's, in other words, if we put more structures on this source, then it could be lifted to another homology theory, such that from that homology theory, and if we compose that with some kind of natural transformation between this homology theory and this homology theory, that recovers this order reconstruction. That's called refinement. Okay. All right, let me go back to what I want to say here. So, right, we want to do it in 2 steps. The first step is find some kind of universal theory to be a host of, say, fundamental classes of Gromov-Witten theory. So then the statement that I'll explain later is, if you look at this modular space, and let's look at the product of the stabilization map and the evaluation map. The target given by the Mumford space taking product with product manifolds. This defines an element inside the thing entitled complex derived orbifold bordism. So let me write the terminology down and I will explain what it means. So this is the first step. Somehow we just look at this modular space together with this map. It can define some kind of bordism class of this space, topological space. For example, if we're in a situation that the modular space is a smooth manifold, and also the tangent space has a stable complex structure, then it does produce an element inside the complex bordism group of the base. So this is the first step. The second step is to construct electric transformations between this version of generalized homology theory to other things. So of course, using this multi-value perturbation or Pardon's technique, we can produce a rational value virtual fundamental cycle. It could be organized to a natural transformation between this kind of version of homology theory to the homology theory over Q. So this is one possible way of doing things. And it might be possible that the target is actually given by, say, Z, or maybe the ordinary complex bordism. So, and this is exactly the approach I'm going to take today. So I'm going to define some kind of integral value Gromov-Witten invariant by these two steps. And now I'll just tell you what these two steps are. So any questions before I do that?
You're going to explain this omega C dart thing as well?
Yeah, of course. That's the key object. Yeah. Oh, that's not from Zoom, so there's people from outside. Okay. So now let me explain the definition of complex derived orbifold bordism. So Abouzaid wants to call this Cornish bordism. Maybe that's a better terminology. So because it's shorter, so it's the better. So right. Now let me tell you what derived orbifold bordisms are. So definition on a derived orbifold bordism chart is a triple DES, where D is a smooth orbifold, E is a smooth orbifold vector bundle, and S is a section locally modeled equivariant sections if you look at the corresponding orbifold charts. So this is definition of derived orbifold chart, just this triple. And we call this triple compact only if the zero locus of this section is compact.
You don't see any transistor here.
No, nothing. Okay, so this is the definition of chart, but somehow we just care about, of course, in the topology or geometry of the zero locus. It's possible that different charts can more or less capture the same information along this zero locus. So now let's define some kind of relations between pair of orbifold charts. So let me introduce some relations here. So the first thing is called the restriction. So the picture you should keep in your mind is, let's say this is our ambient orbifold, and this is our zero locus. And because we just care about the geometry of the zero locus, we should be free to restrict ourselves to an open subset of this ambient orbital D, which contains the zero locus. So in other words, we define a relation for the following. So for an open subset of B containing the zero locus, we declare that this chart is equivalent to, say, the ambient space replaced by this open subset, the vector bundle replaced by the restriction, and the section replaced by restriction on the corresponding open subset. So that's called restriction. And the second relation I want to introduce is called stabilization. So what does it mean? So let's say we are given another orbi vector bundle, defined over our ambient orbifold. And then from this, together with the given dual orbifold chart, we can produce a new dual orbifold chart in the following form. So the total space, the ambient orbifold we are looking at is given by total space of this.
So when you write orbi bundle, that is the first one you started with? Or?
It's another one. So I'll be true one. So I use E prime, so prime is too small.
Okay.
Yeah. Okay. So right, we replace the D by the total space of this new orbi vector bundle, and we look at the pullback of the ordinary vector bundle as part of data of the orbifold chart. And then we can construct a section here, which is the tautological section. I think, of course, there's also direct sum with this E prime. So yeah, it's terrible. Let me write it again. So the ambient space is given by this new orbi bundle, and the orbi bundle living over there is given by direct sum of the pullbacks of these two vector bundles. Then we can make a section out from this by looking at the direct sum of the pullback of the ordinary section here, together with the tautological section for this pair. Okay, so this is called stabilization. So in some sense, this process allows us to thicken up our moduli space one more time so that we can maybe take advantage of this. Sorry, I should say this is required to be equivalent to construct.
Okay, so you have two pies, pi prime and pi.
No, there's okay. This should all be pi prime. Right. We pull back vector bundles defined over D using the map pi prime. Right. Okay. Then the third relation is called Coborism. So I'll just draw a picture rather than write down the words. The thing is, we look at
Just part of the zero section of E prime, right?
part of zero section of E prime.
So
Yes.
the zero locus.
Yes. Yes. Mhm. Yeah, it is same as previous one. Okay, so if I look at Coborism, it means that we are looking at orbifold with boundary, the twiddle, together with the orbi vector bundle and the section living over there, such that its restriction to the two boundaries are given by this, and then we declare that they're equivalent to each other. So, right. These are all the relations I want to introduce here. So they're of a chart together with three relations. And we want to module all these relations to define something.
Would there be not a couple of set theoretic issues? So
Yeah.
would you not have a notion of isomorphism also, or something like that?
Yes. So I think if you set up the theory of orbifold in the proper category, so such issues should vanish. So isomorphism. Yeah.
Because everybody says, well, we have the boundary Z in principle.
Yeah. Yeah, maybe let me say that we fix an embedding of our D1 into the boundary of this guy, such that this guy induces an isomorphism between orbifolds. So this is part of data. Okay, so yeah, this is about derived orbifold, and now we know what Coborism between orbifold charts are. And now let me explain complex.
What's the derived part of the construction?
Yes, that you have an S there.
Yeah, because we have a Gaussian space there together with a section that's
the derived.
yeah, that's a derived thing. So
But now you should have certain operations like taking disjoint unions and these kind of things.
yes. So this union defines this kind of additive structure. Products define this multiplicative structure. So yes, we can define it. But anyway, so let's explain complex or stable complex. It means that, so we still look at this chart. Then we have two vector bundles there. The first one is given by the tangent bundle of the ambient orbifold. The other one is given by this orbit bundle or obstruction bundle here. It's called stable complex if it admits a lifting. Okay, to K0. So in other words, there exists a orbit vector bundle defined over D such that the direct sum of the tangent bundle with this vector bundle F and the direct sum of E with F admit complex structures. So that's called stable complex. And now I can finally make a definition of this symbol Barish asked before, omega bar C dir star. Yes.
So it doesn't matter what it is, it just matters that there exists a
Yes.
structure.
Yes. Yeah, because we have different ones, they're all related by stabilizations. That's why we module out with stabilization equivalents. So suppose Y is our topological space. And this complex derived over bordism is defined to be a tuple of 4 elements such that this guy defines a stable complex derived orbifold chart. And F is a continuous map from this ambient orbifold to the target topological space. And we module out the relations I introduced before. But of course here, for Coborism, we do not include the map as part of the data. So for that, we require that there is actually F twiddle here extending the corresponding maps on the boundary.
Can you say that? Can you say that again?
Right. So
Maybe you start one line beforehand. So
Yeah, right.
Okay, so
So this is defined to be the equivalence class of tuples of the following form. So the first three of them defines a stable complex derived orbifold chart, and F is continuous map from our ambient orbifold to the target topological space. So that's kind of equivalence at this moment. Now let's introduce equivalence, this kind of relations we want to module out. They are given by, say, we replace this chart by its restriction together with the restriction of the map on the ambient space. Stabilization, because I mean we can always project things back down to compose with the given map F. And for Coborism, there's another piece of data we need to keep track of, that's the map itself. So we require that the Coborism between this kind of foot tuple should include a data F defined over this thing with boundary extending the things already defined on the boundary.
So you basically define germs of things around.
Yeah, you can do that.
So this is what you're doing with the restriction.
Yes. But I mean, of course, we can just take a limit in the construction, but I'm satisfied with this definition.
Okay, I'm just trying to understand this as well.
and I have a question. So this is DES. So they would be oriented. There would be a different theory if they're oriented, or?
Right. So if we just require it to be oriented, and I think in John Pardon's notion,
but here in your business, you would not require some orientation about DES or something like this.
So our current to be stable complex.
Oh, okay. So
Yeah, stable complex.
Okay.
Right. So that's why we put a C here. So the traditional model you should keep in your mind is, let's forget about the objection bundle together with the section. So the thing we want is just say an orbital or even manifold. So the requirement is this tangent bundle is stably complex. And when we define these kind of relations, we want to keep track of this stable complex structure. Okay, so after this definition, let me say that there's a statement by Pardon telling you that this defines a generalized homology theory. Yeah, maybe there's some kind of functoriality, like that sequences you can prove, or homotopy invariants, things like that, for such a definition. Okay, so now I can finish explaining the first step here. This is a result of Abouzaid-McLean-Smith. It says the following. So there exists a derived orbifold chart, which is stably complex together with a map lying inside this corresponding generalized homology theory of the de-Montfort space of genus 0, taking product with products of the target manifold, such that the zero locus of this derived orbifold chart as an orbit space is isomorphic to the de-Montfort space, the Euler space of stable maps, if you choose this almost structure J, such that also there is some other such that. So if you consider this F, when restricted along this zero locus, it coincides with the stabilization map and the evaluation map. Moreover, in their construction, there are a bunch of data, but by the end, this element is really well defined. So independent of data. Yes.
Why doesn't on the rows the map in A define already an element in there? This
One of those are.
so I mean you start with this data, right? And you say,
Yeah, but this modular space might be a mess.
but where's the smoothness in this DSF?
Because they constructed.
Yeah, they show that there is
That's
a smooth guy. That's a statement.
single chart Cohomology thing.
Right. There is in their language, there is a global coordination chart, and they can put on that a smooth structure, such that if you forget about all the smooth structure and they go back to orbit space level, there is isomorphism that is falling for.
Okay.
Yeah, the main point of the theorem is there is this global coordination presentation of your moduli space.
I see. So this isomorphism is this orbifold.
Orbit space.
Orbit space.
Right. So this is about step A, and I have to remark that their result works for genus 0, and there's work in progress of Mohan and student Abouzaid-Smith, Amanda Hershey, that can generalize this to higher genus cases. Okay, so now if we have an object here, so if we can construct some kind of natural transformation from this general homology theory to somewhere else, we can try to compose this with this natural transformation to define some other versions of Gromov invariants, and that's exactly what we did. So theorem was an archive early this year, and it says that there exists a natural transformation between generalized homology theories so we call this FOP, means that it's inspired by previous work of Fukaya-Ono, Parker. This is Brett Parker. So it has source given by complex derived over bordism with target given by homology theory over Z. Let me tell you roughly what it does. So,
Can I ask something?
yes.
Is there a transformation from omega u to omega c there?
That's just inclusion.
It's just inclusion. And is that like, does it commute when you write this, for instance, when you compose this with the map to HQ?
Yes. Okay, go back to the statement. So I'll just roughly it means that we look at the Euler cycle restricted to the isotropy free part. And there's a remark. So in fact, we actually have families of this FOP map. So this is like the free part. Gamma for these kind of versions, you look at this kind of locus on whose stabilizer it is isomorphic to the group gamma. So gamma is a group here. For that group. So this is just a special case of our construction because it just looks at those contributions from, say, curves with trivial isotropic group. So let me write down a quick chloride before.
So can one see, so when one looks at the Q, the original Q value stuff,
Yes.
can one, so is there decomposition of this?
Yeah, that's our work in progress, yes.
Okay, so that should be, you put the garbage in the Q and then the remaining stuff is the Z and that's good, yeah? So is it something like philosophically like this?
Yeah, philosophically that's the case. And also we can have a formula decomposing these Q pieces, these Q into pieces, which are Z divided by order.
Yeah.
Yes.
But should I think of like there's a Z locus inside your moduli or something?
Yes, more or less.
Free locus.
Yeah, that's just those curves with trivial stabilizer.
Right.
Okay, let me run a quick corollary. So from this model spaces of genus 0, of course, by this collaborator, we can do it for higher genus as well, or we can construct a z-valued invariants, or what we should call Gromov-Witten type invariant, and the proof is so AMS plus FOP. So very powerful two group of people. AMS produces an element in the derived orbifold bordism, and apply FOP perturbation, we will get an element in Z. Okay. And then to define invariance, we can just pair that with cohomology classes obtained by from pulling back things using the evaluation map and stabilization map. Okay. So let me write two remarks. So there are some applications of this construction, but I won't talk about them in detail, but let me tell you what they are. So the first thing is there is this recent result also by Abouzaid-McLean-Smith telling you that if you look at a Hamiltonian fibration over S2. So in other words, you can, by looking at the Cauchy map, it suffices to look at element in the fundamental group of the Hamiltonian diffeomorphism group of your symplectic manifold. So they say that if you look at the cohomology group of P over Z, then it actually splits in the sense that it's isomorphic to the tensor product. The cohomology of S2 and the cohomology of the fiber. Of course, we can do this for actually a mu, namely the universal, well, it's complex Coborism, right? Sorry, upper star. I talk about Z because our method could give a proof of this. So our result approves without, they call this kind of chromatic lifting. So for experts, the idea is people know that to construct the splitting of this form, it's based on studying this kind of set of representation of your fundamental group of Hamiltonian diffeomorphism group. And this theorem over Q was a result of MacDuff. You can do that because you can construct other representations or over this kind of cohomology ring with Q coefficients. And now because we have a Z variant of this thing, we can more or less, in spirit, construct set of representations over this Z version of quantum cohomology. And so this traditional argument of splitting things using set of elements also work here. And the second remark is okay, it should be possible to do this for Floer theory. So it should work. So in other words, let's say we have a Hamiltonian, and let's produce Floer theory defined over the universal Navikov ring with Z coefficients. And yeah, one can make this definition, and we can compare this with the homology of ordinary manifold with the same coefficient. And you can compare them, you can prove some result. Minutes. So yeah, so maybe let me try to tell you why this thing could be true in a simple case, and I'll tell you the difficulty in making some kind of local picture into a global picture. So before I do that, is there any question about the statement? Okay, great. So let's see. Let's look at the. Okay, let's look at local picture. So what do? We have an orbifold, and it's also required that this chart has a stable complex structure. So to simplify things a little bit, we can just look at, say, so gamma is a finite group, and V is a finite dimensional complex representation of gamma. And I also assume that this representation is non-trivial, so it's a faithful representation. And let's also choose W also to be a finite dimensional complex representation. So in this picture, our ambient orbifold is the quotient of this vector space by this linear action. And our vector bundle would be the induced orbivector bundle given by this equivariant vector bundle. So this is a local picture of what we want to do. And then the goal is to construct a section such that it's, if we look at, so let's call this section S. The zero locus, and we just restrict ourselves to the parts where the isotropic groups are trivial. This could define, or passive exposure defines the homology class. It is, of course, interpreted in a suitable way because we're in the non-compact situation. And in a manifold setting, we know that there is this general position argument that allows us to really choose a generic section such that its zero set is a manifold, and then the fundamental class of manifold is the thing we really want. But now we are in an orbifold setting. And but there is a way to resolve this problem, at least under some assumptions. That's the result of Fukaya-Ono. So what do we do? So they look at the space of polynomial maps of degree at most d, which are gamma equivariant from V to W. Then their claim is for d sufficiently large, for any p inside here, generic. The zero locus of this polynomial restricted to the free part is a smooth complex algebraic variety. So why is this good? It's good because why good? Because it's a complex algebraic variety. If we take the closure for this guy, then we look at this boundary of this zero locus, there will be a real good dimension at least 2. So in other words, the inclusion here defines a pseudo cycle. And when strictly interpreted, it defines the homology class. That's their idea. And let me tell you a Y-line proof of this. So remember that we assume that the V is a physical representation. So V faithful. Then there is this D sufficiently large such that if you look at W as a gamma representation, it could be included as a direct summand of the symmetric power of the representation V. That's a fact from representation theory. And you can prove it if you are bored. And then by standard star argument, star theorem argument, give you all those propositions. So that's all they did in their paper. So we have local picture, and locally we can make it work. And but it doesn't give us a construction of that form. So let me tell you the difficulties in general. So the problem is really about removing, say, so it's about dependence. Here, to make this construction work, you need to choose a cutoff degree D. So maybe a generic element for cutoff degree D is maybe no longer generic, but cutoff degree D plus 1. The second issue is over here we are in a good situation because there are, in some sense, if our group is simple enough, there are just 2 strata of this group action, in the sense that 0 is the only fixed point of this group action, and the group acts on the complement of 0 freely. But this is too good to be true in general. We have different groups, and we have to keep track of how this kind of generic behavior would behave if you change a group. And the solution, the tool we use is to study some kind of Witten stratification. On the universal zero set defined by this formula. So we call this a canonical. Such that, so transversality, we need to verify is actually the version with respect to this really stratified guy. And also, this canonical stratification behaves well in a sense as in some sense preserved under the degrees and change of groups. So in the end, what we want is transversality is really open condition, and then we can just do the Euro cutoff argument in different topology to construct our data perturbation. And I think that's a good time to stop. Thanks.
Thank you very much.
Any questions? So this would be the stratification by isotropic groups, or
it's a refinement by that.
for
So for any algebraic variety which is not necessarily smooth, we have a Witten stratification which is the minimal one, such that each sum is a smooth algebraic variety. And now we have variety with a group action. We need a minimal one with which also respects this kind of stratification induced by the group action, namely the one including my stabilizers. So, but there's also minimal one in this sense. So that's one we take.
I'm thinking like geometrically. So say I have some moduli space of spheres or whatever.
Okay.
Like manifold. So I compactify it, and then I may see sort of multiply covered bubbles.
Mhm.
Should I think of that piece as sort of like the Q piece and sort of the piece in the interior as the free piece in which I mean some sort of
Yeah, the idea is you can try to perturb your Cauchy-Riemann equation abstractly, so that all those curves, say with non-trivial isotropy group, actually be contained in the locus with codimension these two. So as in the case of semi-positive manifolds, you know that could be done.
right.
Right. But in general, you cannot just perturb J to
you
make
can only do this with multiple.
yeah.
But based by the stratification, I guess it gives you a direction, like what you push in there. That's
Yes, exactly. Right. For each stratum, we have a construction of this form. And then if you can somehow sum up their contribution, then that gives you the decomposition of the Q value guy.
And also, so these are supposed to be, maybe I missed it, but these are the gamma equivariant polynomials of 3D
Yeah, I'm most deep.
At most D.
Yes.
And then when you want to apply it for your section S, S could be whatever, it doesn't have to be like.
Yeah, it could be whatever, but
you can
somehow.
approximate it by solution
Yeah,
of a
exactly.
polynomial.
Right.
And this is basically what you're using.
It's more than that, but there are a step of approximating things using polynomials. So something can just use polynomials to. You just need to result at a level of polynomials rather than general ones.
Questions? You have a question for your co-host?
Sorry.
Do you have a question for? Okay, so let's take our speaker.